All right. So, as I was saying before I started recording, I actually think chapter 11, mathematically wise, I think is the easiest chapter. All right. There's a lot of the stuff is just going to make sense. Like, it's not like crazy things that you have to try to remember how to do. Like we were doing this surface area formulas and volume formulas, and you got to remember those formulas or write them down and look at them. And there was crazy integrals and stuff like that built into it that you had to do. So there's less of that. And actually, the vast majority of the questions that you're going to do, it's in essence a true and false question. You're going to tell me if it converges or it diverges. That's actually the answer to the majority of the questions in the homework and on the test. It's just a matter of how you determine if they converge or diverge is really what we're going to spend most of the time trying to figure. So, no. You still have to show your work, and if it's just the answer, I won't give you credit for it. We're going to talk about two different things. They sound very similar, but they do mean two different things. We're going to look at sequences and series. Okay, I know they're both S's, and they're easy to mix up. A sequence is a list of terms, a list of numbers. A series, which we're going to talk about probably later in class tonight, is a sum of those terms. So that's where you see that summation symbol before things. That is a series. Yeah. A sequence is just a list of terms that we have. Anybody know a sequence off the top of their head? Yes. Fibonacci sequence is probably the most famous sequence that people know. And he literally, as crazy as it's going to sound, according to his history, he actually came up with it really by looking at rabbits. As much as people think, no, that's what is in his, like, not necessarily his memoir, but his biography and everything else, is that he literally came up with that by looking at how rabbits breed. The Fibonacci sequence is 1, 1, 2, 3, 5, 8. It's adding the two terms previous to it. It is known as a recursive sequence because you need the other information before it to figure out the stuff after it. Not all sequences are recursive. A lot of sequences, we can come up with a formula for them to come up with those values. So an infinite sequence is just a sequence that goes on forever. Typically, we're writing them as A to whatever term number that is. So A1, A2, A3, all the way through AN. You can do AN plus 1, AN plus 2. Those would be those extra terms. And we're going to look at some of that notation in a little bit. All right, so let's look at a couple just regular sequences. So the first one here, this is 3 different ways to write the exact same sequence. You can just write it as 1 over 2 to the n. Okay. Notice the brackets around it. That designates that it is a sequence that goes on forever. Sometimes you'll see, like you see down the next one here, you'll see the terms. You'll see n equals 2 to infinity. That tells you where you're starting and where you're going to. You do not have to start at 1. A lot of sequences do start at 1, but you do not have to. We can write it as an equals 1 over 2 to the n. That an automatically means we're looking at a sequence. Or you can list out a list of values for them. Okay. Any questions with the, because you're going to see a variety of different ways that they're going to write it. So it's just a matter of making sure you know those all mean the exact same thing. All right, so let's look at this one. Let's look at we're going to come up with the first 3 terms of it. So what's the first term?
Yeah. 1/2.
It's going to be 2 over 3. Because remember, we're starting off at n equals 2. So n is 2, 2 plus 1 is 3. What's the next term? Yep. And the next one. And it just keeps going. Okay. This sequence here is written very similar to the one we just did, except there's a little bit more information in it. One of the things that I want to mention in this one, and why I put it, was that right there. The -1 to the nth power. That automatically designates it as an alternating sequence. So your signs are going to change, okay, for every one of them. Depending on what you want your initial value to look like, depends on how you set up your alternating. So if they're going to alternate, it's going to be negative, positive, negative, positive. You're going to have -1 to some power. If you want the first one to be negative, if you set it to n+1, it'll be negative. If you want it to be positive, you typically set it to n. It's just going to change on how it looks like. So in this case, we're starting off at n equals 0. So what is the first term? Nope. All right, so what's -1 to the 0 power? That's 1. What's 0 plus 1? 1. What's 3 to the 0 power? 1. So my first term is 1. Please remember that anything raised to the 0 power is 1. That is extremely important and comes up quite often in sequences and series. All right, what's the second term? It's -2/3. What's the next term? 3/9. What's the next term? So 3 to the, so this was n equals 0, n equals 1, n equals 2, n equals 3. So this would be 3 to the 3rd power, which is 27. And the next one would be 5/81. And it just keeps going. So far, so good? Okay. All right. What's the formula for a to the n, or a of n, I should say, or a sub n? All right, so when we're looking at these sequences, look at them in pieces, okay? Don't necessarily look at it as one thing that you have to come up with this perfect thing for. Look at it in pieces. You can always simplify and break things down a little bit later if you need to. So what's one of the first things we notice about this sequence? Okay, so it is alternating, right? So I know I'm going to have -1 to something. Okay. So, and the first term is positive. So I want my first one to be positive. So let's do n+1 for right now. So we're going to assume, since I did n+1, that that's the first term, that's the second term, third, fourth, and fifth. Okay. You don't have to start at 1, but in most cases, starting at 1 is a good place to start. If you have to start at 0, we can always change things afterwards to fix that. But a lot of times, starting at 1 typically makes your life a lot easier. All right. So you said something about the bottom. Right. So if I did 5 to the first, I get 5. 5 to the second is 5 to the third. So that works, right? So my bottom is going to be 5 to the nth power. And the top is just n+2. And there's my sequence. Okay. So it does not necessarily have to be something crazy complicated. It'll work. Because then you have -1 to the second power, which is positive. That's why a lot of times, if you're going to do, if you want it positive first, you do n plus 1. You want it to negative first, you do n. Because if you're starting off the first n equals 1, it works. Good. Anybody know what this is? Yes. That's E.
The letter, I don't know.
I would have done pi, except I honestly don't know pi to that many digits, and this one was in the book. Not every sequence has an equation. E does not. E is just like pi. It's an irrational number that goes on forever and never repeats. So not every sequence is going to have an equation for it. So there is no AN for this one. Same thing with Fibonacci sequence. Fibonacci sequence, I cannot come up with an A to the N. Like this one right here, I can come up, if I told you I want the 10th term, you can plug 10 into that and get that equation, get that answer. No questions asked, because you have the equation for any term. Fibonacci sequence, as we talked about, is recursive. So I can't ask you for the 20th term in the Fibonacci sequence without you having to literally find all 20 terms. Okay, yes. For E, which is what that is. Well, 2.7182818. That's actually E. This is, there is no equation for E. It's E's like pi. It's an irrational number.
I get that, but like, how do you recognize that?
Honestly, most of the time you look at it and goes, like in this case, she's going, okay, +6, +7, or no, -6, +7, +6, plus. It was like, there was just no, right? There was just no pattern that would work out for it. So it's going to be quite obvious that like there's just nothing that's going to work for this. The nice thing is the vast majority of problems we're not going to deal with things like that. The only reason I bring that up is because I want you to understand that there is sequences out there that there is not numbers for. Okay, so like even looking at like dates and stuff like that, like sequences, if you look at the information I gave you at the beginning, it doesn't necessarily have to be a mathematical one. So the other example I gave you was the population of the world is of January 1st. It goes up. It's not going up by any specific pattern. Yes, we can estimate where it's going to go and stuff like that to figure things out, but we can't find the exact value of it because it's not a specific pattern to it. So, huh? Oh, what did that come up? So those sequences aren't ones that we're typically going to be looking at. Do they converge? Do they diverge? Because you don't have an equation that you're going to figure out. So they typically would always diverge because they're not going to a specific value. Okay. All right. What was your most hated section in Calc 1?
Anything to do with limits or a graph?
Oh, great.
Kind of.
All of it.
So then this will be right up your alley.
Why did
So welcome back to limits. A lot of this deals with limits. because if we're looking at an infinite sequence, we need to look at where it's going to. And the only way to figure out where things go to is to do limits, because we can't go to infinity. There is a few different definitions of the limit of a sequence. This one is just simple and makes sense. There is a very more complicated version in the book. If you want to learn that one, you're more than welcome to. They say the exact same thing. I just think this one makes sense. That's why it's called the intuitive definition of a limit, instead of the exact definition of a limit. So, more precise, as they like to call it. As the limit of n goes to infinity of a to the n, it goes to a L, or the limit of that function. So basically, the sequence goes to L, all right, as we get larger and larger. If it goes to a specific value, it converges, okay? If it goes to infinity or negative infinity, it diverges. All right, so if it's not going to a specific value, it diverges. If it goes to a specific value, it converges. So we say convergent or divergent. Yes.
Write that as the limit as n approaches c, base of n, it diverges. C being like,
No, because you actually want it to go to infinity.
no, I'm saying
Oh.
that if limit of n, the limit of n goes to, I say that if the limit of a sub n, how do I say that again?
The limit of a sub n as n goes in.
Infinity converges, but that's what that is.
Yes.
And for the diverges, how would you write the limit notation for that diverge?
It doesn't. It literally goes to infinity. You would,
It goes to infinity for converge,
no.
but it says n goes to infinity.
Okay. N's going to infinity either way. The answer is what you're looking at. So if the limit as n goes to infinity of an goes to a value, it converges. If the limit as n goes to infinity of a sub n goes to infinity, it diverges. Yeah. Yes.
And what if a sub n doesn't convert from one value to multiple?
It can't.
So
If it's bouncing, then it's divergent, because it doesn't go to any specific value. So for it to converge, it has to go to a specific value. So yes, my going to infinity is a little generalized, because you can't have things that bounce in these situations. And in that case, it still diverges because it doesn't go to a specific value. Yes.
So for the diverge limit, would that be equals infinity or equals like dne?
Yeah, it just doesn't go to a thing. I'm actually going to do a couple right now. I'll show you. So, I want a simple one to start with. Before we do all the rules. This was easier. So let's set as a to the n, or a sub n, is sine of n pi. So if I have the limit as n goes to infinity of a sub n, what is the sequence going to come out to be? So let's look at the sequence. If n was 1, what's sine of pi? What's sine of 2 pi? What's sine of 3 pi?
Also, how do you want
so if you think
That
of a
keeps-
circle,
Wait,
2 pi is half the circle. Sine is the quarter. So if you go 1 pi,
that's negative 1. Oh, it's 0, actually.
that's going halfway up.
It's like,
And
oh,
they did just-
Actually, in this case, this one, sine of pi is 0.
Oh, yeah, you're right.
Sine of 2 pi is 0. This one's zeros.
Oh, my bad.
So what does the limit go to? 0. You're thinking cosine, which honestly I thought of when I wrote the problem, but
No, I thought of it as, pi over 2 for a hot second.
oh yeah,
So
yeah, cosine of
Totally goes all the way across.
Yes. uh,
Sitting back there cranking out all these numbers. I'm like, where do you know? How do you know this?
yes.
is the arrow, should it be the arrow or should it be an equal sign?
In that case, it actually equals. It just, I typically write my limits as goes to instead of the exact, like it's that exact value. So I typically write goes to, but in this case, because it equals 0, you can put equals 0. Either one would be acceptable to me. It depends on how you're writing it. And when I've written so many of these, most of the time I'm saying the limits of this is going to that value because it's never, even if as it goes to infinity, you never can actually reach infinity. So it's that weird situation at the end. What's cosine of pi? No. Cosine of pi is negative. Cosine of 2 pi is. Cosine of 3 pi is. And this keeps bouncing. So this one does not exist because it bounces between -1 and 1. Okay. So we're going to look at a lot more that are more algebraic, that we're going to figure things out. Actually, very similar to what you did when you did the stuff for derivatives at the beginning, except we're not going to have to do the whole derivative equation and all that other stuff. So, all right. So there was one equation that you did in Calc 1 that becomes the most important part of this. Is this one. So 1 divided by n to anything, any power, will go to 0. As the bottom gets infinitely large, the fraction becomes 0. That should just make sense. Everybody agree with that? Good. All right. Because that was actually the way that you, so when I taught this in my Calc 1 class, I go, okay, you have pre-calc brain and calc brain. Pre-calc brain, when you were doing the end behavior, we're going, oh, it just goes that way. You're looking at the highest degree and stuff like that. Calc brain, you have to divide everything by x to whatever power that's there. Same concept. So if we divide things by the highest degree, we get those things to go to 0 and they eliminate themselves. All right. Actually, I should copy that other part. So you have all of this. All right. Here are the limit rules. You should have seen these before, but they also work for sequences or sequences. So these again should not look out of the ordinary. The addition and subtraction ones are the same ones you saw in the derivative ones, the constant ones, same thing as derivative ones. The multiplication division ones were not art of derivatives because they had specific rules for those. They do work for sequences though. However, A sub n and B sub n both have to be convergent sequences for these to work. If one of them is divergent, then these sequences do not work. Because I can't have divergent times a convergent. That doesn't make sense.
Is there like a big picture way to explain that?
What do you mean?
Like I have no idea like why
Why we're doing?
you know this. Like,
Oh, I'm going to do those.
what does it have to do with-
We're going to get there.
Okay.
I'm giving them to you
I'm not
because
retaining any of this because I don't know what it.
no, that's fine. I'm giving them to you right now because we're going to use them in a minute. It's just I can't literally do the very first problem without actually you understanding that I can split this apart. Well, I guess I could and then just assume you knew that part, but honestly, this stuff, once we start doing the problems, you're never going to go back and go, oh, I'm using the sum rule or the difference law. You're just going to do it. So we have one more, and I don't know why they didn't put it in the same table, but that's okay. The power law also works, so I can take things with exponents and pull the exponent out. That in a little bit. All right. Now let's do one. All right. Oh, sorry. Finish. Okay. That's fine.
Is this concept isolated towards count two, or is this something that you could expect to see count three?
Trying to remember. You typically don't see series and sequences too much in Calc 2 or 3. You'll see like power series and stuff like that. When we start to get towards the end, when we look at power series and like Taylor-Maclaurin series, they come up with a mathematical, like an equation way to find things, or they use series to estimate equations and polynomials. And that you might see where they're actually using the differential or the integration on those type of things. So it's possible. You're not going to see as much of the sequences and series stuff that we're talking about, though. It's more of the Maclaurin and Taylor series. All right. So does this converge or diverge? So to make this is how you would do it. I'm going to write it how I'm actually, you know what? I'm not even going to write it how the book does it. I'm going to show you how the book does it. And then I'm going to show you how you're actually going to typically write this. So this is using all those limit rules. Because I don't feel like writing out the steps. Okay. So what you're going to end up doing is going from basically here to here. You're going to skip this whole thing together. All right. This is all those limit rules that we just did. Because it is addition, division, we can split this up and you could look at the limit of each one as it goes to that piece. So you're not looking necessarily as the whole limit thing goes to, you're looking at the limit of each piece goes to. So the limit as n goes to infinity of 1 is 1. That's still 1. We've divided them all by n's. That's why we were able to get that division one. That goes back to that very first thing that we looked at up here where I said the limit of 1 over n to whatever power it is goes to 0. That's my goal, because if I get zeros, I can eliminate things. And in this case, that 1 over n goes to 0. So n over n plus 1 goes to 1. So this sequence converges to 1.
But you're gonna, have us show like all that work on the test.
I don't need to see that stuff. Okay, that one again, that's using those rules. That's why I said most of these rules, once you start doing the problems, you're not going to break them down into those things. I just needed to show you that you could do that. So when I do this, you understand why I can look at the limit of each piece instead of the whole thing. Yes.
Why is it necessary to divide by n? Why can't you just do the infinity as is?
So then if I looked at the original problem here, I have the limit as n goes to infinity of n over the limit as n goes to infinity of n plus the limit as n goes to infinity, or not 8, of infinity of 1. What's the limit of as n goes to infinity of n?
Just
Right. So then I have infinity over infinity plus 1. I can't do that. That's indeterminate. That's one of those indeterminate forms because I have infinity over infinity. I can't go infinity over infinity as 1. So because that, one of the methods that we have to eliminate that option is by dividing everything by n, which algebraically I can do as long as I do the same thing to the top and the bottom. I eliminate that indeterminate form. Okay. There are other ways to do that, which we will look at in a few minutes. This is one of the easy methods to do it. And that's actually the method you learned in Calc 1 when you were looking at the original things. You divided them all by x to get rid of those to figure out where it was going to. So in this case, this series converges. And L equals 1. All right, so we want to see if this one converges or diverges. So I have the limit as n goes to infinity of n over the square root of 10 plus n. So what am I going to divide this by?
Just set, like, cause just looking at it, you, like, let's say I put n equals 15, right? So I'd have 15 on top, the bottom would be 5. So,
Okay.
So it equals 3, right? So if you keep doing that, theoretically, the higher number you get, the more it goes to infinity. But can I say it like that, or do I have to show a rule?
You have to show a rule. Well, you don't necessarily have to show a rule. You have to show what happens as it goes to infinity. You can't use a few different examples and stuff like that to be able to show that it goes to infinity. Because, and don't ask me to come up with them because I'm not going to come up with that off the top of my head. Not every series does the same thing as it starts as it goes off to infinity. Crazy things can start to happen later on. So that's why you don't want to just pick and choose numbers. Yeah.
Would getting rid of the radical in the bottom be a start?
How would we get rid of the radical in the bottom?
You would multiply by 1 bottom radical over the.
Rationalize.
Oh, you're rationalizing the denominator,
Because that would get rid of it in the bottom, but then you have.
but then I have it in the top, so it's really not going to help me there. The only method that I've shown you so far to use is dividing by n, right? So try that first. If it doesn't work, then we'll try something else. Yeah.
If we do what you did, right, rationalize it and put the square root on top, technically it'd be n to the power, so it'd be 0,
It wouldn't be n to the power.
it'd be over 1/2. N to the 1/2.
You'd still have the 10 plus.
No, he's not. He's multiplying the top and the bottom by 10 plus n.
Oh, never mind.
Because you can't raise it to like the 1/2 power because that's not doing the same thing to the top and the bottom. Because that would change the problem. So let's just divide the top and the bottom by n. So my top is now n over n. If I divide the bottom by n, how would I get that inside the square root? I would square it. So 10 divided by n squared and n divided by n squared. Yes. Because so I need to make the bottom, so I need to make the whole thing square root, the square root. So if I have square root of 10 plus n over n, I need to change this to 10 plus n over the square root of n squared. Those two are the same thing, right?
Yeah.
So now I can put it together to be one fraction or one square root. A lot of times, you typically probably saw this the other direction. When you had a problem like this, you did the square root of 4 over the square root of 9, which is 2 over 3. I'm just going the other direction and putting them back together. No? So square roots are like a power. So it's like if it was like n squared over m squared, that's the same thing as saying n over m squared. Those two are the same thing. Square root's no different than a power. So I could still do, it'd be n to the 1/2 and m to the 1/2, which would be n over m to the 1/2. Same concept. All right. So now we have that. So let's look at the limit as n goes to infinity. What's n over n? 1 over, what's 10 over n squared? What's n over n squared? So this is 1 over 0, which goes to infinity.
Isn't that more so Danny?
So remember, it's not 1 over 0. It's the bottom is getting, as n goes to infinity, the bottom is getting closer and closer to 0. So as the bottom is getting closer and closer to 0, the bottom is getting closer and closer, is getting smaller and smaller, which makes the fraction go to infinity. Okay. So when we were saying 10 over n squared is 0, right?
Yeah.
We're saying as the limit of n goes to infinity, it is going to 0.
Yeah, I get that.
So this isn't 1 over 0 as in like an indiscriminate does not exist type thing. This is 1 over, as it's getting closer and closer to 0, what's happening to this fraction? That answer is going to infinity. Because the bottom of the fraction is getting smaller and smaller and smaller.
It needs to be 1 over a variable. The variable goes to infinity, then that whole thing would go to 0.
But it is over a variable. It's 10 over n squared plus n over n squared.
Would it be, is dropping the notation, is that, Cause that'd be wrong.
Well, you wouldn't want to write it because you're still doing the limit as it's going to that. So
So.
this is where those rules come into play.
So you should write the limit notation at each stage.
Well, and this is why in this problem, they wrote that. So it's not saying that right there, that is getting closer and closer to zero as it's going to infinity. So in this step, I've done my limits, which is 1 over 0, but I got to realize that that is at infinity. So as I'm getting closer and closer to infinity, that number is getting closer and closer to 0, which means this is going to infinity. I'm not dividing by 0. I'm dividing by an ever increasingly smaller number.
So it's the limit as n approaches infinity of 1 divided by the limit as n approaches infinity of 0.
Well, it's the limit as n approaches infinity of 1 over the square root of the limit as n approaches infinity of 10 over n squared plus the limit as n approaches infinity of 1 over n. That top, that way, goes to 1 because there's no variable left. This down here is getting smaller and smaller and smaller. So as we get all the way to infinity, it's going to 0. But right before we get to infinity, it is an insanely small number. And what is 1 divided by an insanely small number?
It's just like when you get the final number, it's not, because that's not what I learned in calc. That's not what I learned in calc. In calc, if it's 1 over 0,
It's undefined. Absolutely. But
and I'm talking about within the context of the chapter where we were learning about limits.
okay. So, but you, and actually you didn't, but that's okay. It's so if you had 1 over 0, that is undefined. Absolutely. We don't have 1 over 0. Okay. And I think that this is the disconnect. We don't actually have 1 over 0.
Is there a different way to write it other than 0?
Yeah, the way I just wrote it there, with the limits as n goes to infinity of 1 over n.
That's what I was saying earlier with like plug in.
So
Plug in those numbers, it helps me like visualize that. What you're
I can't. So even 1 over infinity, you can't do. When you were looking at that calculus, if you had something 1 over infinity, you can't do it. You were told that 1 over infinity is basically 0 because 1 over an increasingly large number goes to 0. That's what you were told to use because if you saw 1 over infinity, it wouldn't make any sense. Same concept here. If you see 1 over 0, I'm not saying it's because we're looking at limits. We're not saying it's 1 over 0. We're saying it's 1 over an increasingly smaller number. So as that bottom is getting increasingly smaller, okay, what's happening to that fraction?
Well,
So if I divide 1 by 1/2, it's going to get small.
Yeah.
It's going to go 2, 4, 8. It's
higher
gonna,
and higher down.
right. It's going to
No,
infinity.
I get that.
That's why 1 over 0 is going to infinity because we're looking at it in terms of that bottom is not 0. It's the bottom is getting increasingly closer to 0 as we go to infinity.
That, I'm saying, why is it written like that?
Because there's no other way to write it that like shows that value. There's no other way to write it.
Because the zeros, it's 0.
Right,
If you
but
were
that
to-
0 isn't 0.
If you were to write it as, oh, this is doing something, then you would write it as something else, right?
That's what that is. We got 0 by looking at that limit. That limit is the square root of 0, which is 0. So No, there's no other way to write that. We have to realize what we're doing before that to understand why that's going to infinity.
I always understood limits as like, you have these limits, n going or whatever, and then you solve for it. And then the final answer is like, okay, we're out of the whole limit notation now, we're at numbers now. That's how I was.
Right, but you still have to understand why you still have to understand what you're doing to get to that point. So, yes, we have 1/0, but that's not undefined. And in this situation, that it's divergent because it's going to infinity. Because that number is getting smaller and smaller, or well, in this case, larger and larger and larger. You're just gonna have to accept this one. All right. Where do you work? Where do you work?
Me?
Yeah. Huh? Don't you work at a hospital?
No.
I know.
Oh, that's right. You work at you do
I design architectural.
oh, that's right. You never mind. It wasn't you. It was my other class who also sits there. That's right. You do architecture.
Probably help you out.
You do architecture, but you're doing what is it?
Biochemistry.
Okay.
Has nothing to do with my job.
Yes.
Yeah, no,
Okay.
that's the first time I ever heard of it.
All right. That's right. Never mind. Forget it. What's the crazy guy's name that came up with some theorem that you learned in Calc 1 to help you deal with things like infinity over infinity? We'll help you solve that. So in this situation, if you get something that's going to infinity or that's an indeterminate form, we can use L'Hopital's rule. And that's what we're going to use here. Yes, sometimes you have to continually do it until it figures it out. So in this situation, because I have an ln, I cannot divide by n. Because ln divided by n doesn't mean anything. So it would help me in the bottom, but it would not help me on the top. So we want to use L'Hopital's rule. What was L'Hopital's rule?
Saying, like, you were down, I literally have no idea what you're talking
Literally L hospital.
Yeah,
about.
Oh, without the
Oh, thank you. Now
it actually has the S.
no, it's the circumflex.
Yes, there's a circumflex above it.
Not above the S. The circumflex stands in place of the S. How does
L
Like,
hospitals.
Oh,
just
maybe, yeah.
random.
So, but for how we would write it, we literally write it as L hospital. And we had this massive fight over the book that I just wrote because of this word. And she went through and did like this entire 5-page history paper and explained why it should be written this way. Like, fine, we're going with it. So literally that's the only way because I've had it written so many times.
How do you say it again?
L'Hopital. Because you don't pronounce the S. It's L'Hopital. It's right. You don't pronounce the S,
I
although.
recognized it when you wrote it down. I was
Yeah.
like, oh.
So basically, all this rule says is we do the derivative of the top and the bottom. So what's the derivative of ln of x? Is 1 over n. What's the derivative of n? Is 1. So the limit of n goes to infinity of ln of n, or n, equals the limit as n goes to infinity of 1 over n divided by 1, which goes to what? 1, which is 0.
0.
So this
Oh.
converges.
Done.
Hold on, wait.
Oh, you're fine. I'm not going to.
I have a question.
Sure.
I'm sorry.
No, you're fine.
So in this situation, the 0 is a real 0.
No. In this situation, it's the exact same concept. It
Because if
is.
it was, then that would equal infinity.
No. That number is getting increasingly
Yeah,
large.
but the 0.
That goes to 0.
So in this situation, the 0 means,
As the top is getting increasingly small,
yeah.
over 1 goes to 0. Same concept. It just totally makes sense to you because it's 0 over 1, which is 0. I knew you were going to ask that question as soon as I wrote it. I was waiting for you to ask it. It means the exact same thing.
I just not get it.
No, because you're looking at it in terms of I've eliminated the limit, so now I have a number, and now I'm using my rules of numbers.
Am I still not? Is that not?
It's not, because it's still a limit. You still have to look at as it's going to infinity, which is probably because it's literally some abstract concept. It is very hard sometimes to wrap your head around it because it's not a concrete answer. Okay, you're still looking at this as the limit as n goes to infinity of 1 over n is getting increasingly closer to 0 because the bottom is getting increasingly large. It doesn't equal 0, it is getting closer and closer to 0. It will never actually reach 0. So we put 0 because we need some way to write it. But it gets literally as close to 0 as you can get without ever actually touching 0. If that makes any sense. Yes.
Would you consider this function to convert, right?
Yes, this converts.
But what happens at 1? And hits
What do you mean that hits 1?
1 over 1 is 1.
That's the first term. That's the first term in the sequence, though.
Oh, okay, so it starts there.
Yeah, we're looking at what happens to the sequence as we get to infinity.
Yeah.
So was the last one divergent?
Yes. Oh, I didn't write divergent. Yes, it was divergent because it goes to infinity. I know I said it. I just don't. I must not know. All right. So this says if the absolute value of the sequence goes to 0, then the limit of the original sequence, or the limit of the non-absolute value of the sequence, goes to 0. Okay. Before I go through and do this problem, there's a very important piece to this. Notice it does not say the limit as n goes to infinity of the absolute value of a to the n goes to a letter, a number, like L. It has to go to 0. If the limit of the absolute value does not go to 0, then the limit of the other one does not exist in that situation. And we have to try something else. Okay? That is important. Because, like, I can find the limit of the absolute value of cosecant of theta, for example. That does not necessarily go to 0 because it keeps bouncing. So that doesn't mean that the limit of the regular one goes to 0, whatever it is. So that's important. It has to go to 0. This comes up whenever you're looking at those alternating sequences, those sequences that are going to change signs. Okay, so like this case. So if we look at this, let's look at the absolute value of the situation. That means I'm going to be looking at the limit as n goes to infinity of 1 over n. Because the absolute value, in essence, gets rid of the sign. So 1 over n goes to?
0.
You were asking before why I typically write the arrow instead of an equal signs. That's one of the reasons back to where you were saying before. It's because it's going to 0, not actually equaling 0. Although you'll see the book, always write the equal signs.
In the math book that you're writing, what's it say?
I'm actually most of them I think I wrote to equals just because that's the way that most of them write it. So
Line
Yeah,
just follow
I know.
those.
It's,
What's a new term for this?
I would love to. I don't have I don't have all those doctors and letterings and everything else after my name for anybody to actually listen to me. So. So, but that's the thing. That's why I typically, when you hear me say it, I'll say it goes to 0 because that's what it's actually doing. It's not actually equaling 0. So, all right. So since that goes to 0, or in the book's case equals 0, that means my original limit also goes to 0. Yes.
So this is how you figure out if a sequence that flip-flops actually goes to something.
Correct. If it went to 0, then we could figure that out in this case. If it goes to any other number, that theorem does not work. And we'd have to do something else. Yes.
So if we're presented with a problem where we're not given like the case of F, but we're given a string of numbers, and we have to come up with it, and it's one of those negative, positive, and negative, positive. For us to figure out like the limit, I guess, activity, we would have to apply the absolute value that we're doing here.
Yeah.
Is that a kind of problem that we can expect to see?
Like the next problem I'm going to do.
Oh, okay.
The exclamation point.
Yep. What's the exclamation point mean?
Factorial.
Factorial, which means it's all numbers multiplied to that. So n factorial is literally 1 times 2 times 3 times 4 times 5 times 6 times all the way to n. Huh? So factorial. So if I had 3 factorial, it's 3 times 2 times 1.
Well, I like that.
5 factorial is 5 times 4 times 3 times 2 times 1. You'll typically see it quite often when you do probability and statistics and stuff like that. That comes up quite often. Your counting theorems and stuff. We'll see it in some problems just because it does come quite often in mathematics. All right, so you're asking about, okay, what about a series of numbers? Like this one, there's no easy way for us to sit there and look at this without actually looking at what the series looks like. Okay, because I can't do L'Hopital's rule because I don't have anything for n factorial. It's like there's no derivative for that. So I can't divide it by n because it's not, the setup isn't there to do that. So let's look at the actual breakdown of what the series looks like.
Is there an algebraic way to get rid of factorial?
Not unless you have another factorial. If you had another factorial, you'd cancel things out. All right, so a to the first is 1, or sub 1 is 1. A sub 2 is 1 times 2 over 2 times 2. A sub 3 is 1 times 2 times 3 over 3 times 3 times 3. A to the n is that. So,
Factorial, the next point.
well, that's kind of what you're literally trying to figure out.
I feel like at a certain point, the factorial. Fun.
So, but that's actually what we're trying to figure out. It's like, the concept of which one's bigger is going to tell us which is converges or diverges. If the top gets bigger, then it's going to diverge. If the bottom's getting bigger, then it's going to converge. That's what we're trying to figure out. If the top of a fraction gets infinitely large, it converges or it diverges. Sorry, diverges. If the bottom of a fraction gets infinitely large, it converges. Problem is they both can't do different things. Like if they're both getting infinitely large, then you have infinity over infinity, which is in essence what we're going to have in this case. So we have to look at this a little bit of a different way to do it. So let's look at this. So why did I do that?
Because first thing equals 0, 0 times that goes to 0.
What do you mean?
1 over n, 0, right?
So yes.
They're both 0.
So if I pull out the first one, all I'm doing is pulling out that first one, right? And it's times this whole rest of this thing over here. Okay. So this part over here, what's the biggest this could possibly be? 2 times 3 times all the way over to n times n. What's the biggest this possibly could end up? If you're looking at just this, what do you think this part right here is going to? Trying to think about a different way to ask the question.
Like we're 5.
In essence, I pulled out the first term, right? So I pulled that out. So what's that equal? 2 over 2 is 1. 2 times 3 is 6 over 9. If I did 2 over 3, 3 over, oh no, sorry. 2 over, it's 4 times 4 times 4 times 4. 1 less 4. That would be 64, 24, right? So the biggest this could be is 1. Right? Yeah. So there's another theorem that we haven't talked about yet, which is known as the squeeze theorem. Which you might have remembered from also in Top 1, because you did talk about the squeeze theorem in Top 1 too. So basically it says if I know the series is between two other series and both those other series converge, then I know the series in between them also has to converge. So in this situation, let's write that down. This up here. I know that a to the n, the original sequence, has to be somewhere between 0 and 1 over n.
It's a lot of numbers.
It's not actually. The limit as n goes to infinity of 0 is what? Limit as n goes to infinity of 1 over n is 0. So if these both go to 0, then that also has to go to 0. That's what the squeeze theorem states. So if I know it's between two values,
It's good. I know it's.
Right.
squeezed.
correct, they both go to 0. Therefore, the original sequence that I looked at, since it can't be any lower than 0, can't be any higher than 1 over n, also has to go to 0. Okay. So this sequence converges to 0. Yes.
How would you show the report then? You just say squeeze there. How does pulling out the 1 over n change it?
Because by pulling out the 1 over n, in the very first sequence, I have 2 over 2, which is 1. And after that point, it's never going to get higher than 1.
I thought wasn't first sequence 1
Well, yes. Okay. So,
for the second sequence?
right. Sorry. Second term of the sequence. Yes. And it never gets higher than 1. So that's why
So you know 1 is the upper limit.
yes, 1 is the highest possible you can get. And I know it's not going to go any lower than 0. And since 1 over n is the highest you can get to, that goes to 0. So the way the book actually wrote it well, that's no, I don't want to. Let's do this. They actually wrote it really well, so just I'll do that down. That's literally how you write the answer. There. Yes.
So you have the 1 over n, and so you have to like kind of pick numbers in sequence to see what like does.
For some of them, yeah.
Yeah.
Yeah, for some of them, absolutely. There's no way to this is one of those ones where the easiest way to look at it is to look at the actual terms in it to figure things out. And that's why when you said that, it's like, look, that's the next problem. We're going to have to do that. So yes, sometimes you're going to have to look at those pieces to figure it out. You're not going to be able to look at the equation that we have and get the answer because it just doesn't work that way.
Pulling out like the first term, is that like a strategy, or did
It can be. It's and this one leads into the squeeze theorem, which works really well for this type of problem. It's not the first thing you're going to want to try. It's the first thing you want to try is if I can divide them by n because it makes your life extremely easy. And then like the Hopital's rule, this is one of those ones where when you have like factorials and stuff like that just don't work, or you have something raised to the nth power where it just doesn't necessarily work. Like how do you actually go through and do it?
I get how the squeeze theorem arrive at the answer once you know that you have to apply the squeeze theorem. I just don't know how to recognize that. Okay, I need to.
So a lot of times the squeeze theorem comes up when you have a problem that you already like. It looks similar to something you already know, and then you can apply the squeeze theorem to something else. So let me see if I can find another problem that works with the squeeze theorem real quick. Unfortunately, these are not ones I can just make up off the top of my head. Let's look at that one, because this is a good one. All right. Now, I've already kind of told you that it's going to use squeeze theorem, but it's a good example of why. The squeeze theorem really comes into play a lot of times, especially with your trig functions, sine and cosine, because we know sine and cosine has to be between -1 and +1, always. So it kind of fits really well. And since this one is squared, I no longer have the negative one. It's from 0 to 1. So if I'm looking for the limit of this, I know that cosine squared of n over 2 to the n has to be less than or equal to 1 over 2 to the n and greater than or equal to 0 over 2 to the n. Do you understand why? Right, because cosine's got to be between 0 and 1. Now, this side is 0. So if we look at the limit of each piece, so if I look at the limit of 1 over 2 to the n as n goes to infinity, that goes to 0. So then I know that cosine squared of n over 2 to the n has to go to 0 because of the squeeze there.
There's not a lot of math going on.
No. That's why I said it's most of the stuff that we're going to be doing is, does it converge or does it diverge?
I think with the trig, it's like a little bit more intuitive,
Oh, absolutely.
but the factorial and the
Yeah, that one was a little more complicated on where it is. And the squeeze term doesn't come up often. Like that's one of those ones you use at the end. It's like, okay, I can't think of any other way to do this. The trig one, it fits really well because I know that the trig function's got to be between two values.
and if it was like 2 cosine n, then like that would change the amplitude.
Yeah. But then I know it's between 0 and 2,
Yeah.
and it's still not going to make much of a big difference.
0 less, okay. We should work.
No, I'm just going to give you.
Divide by n first.
We're going to do some problems. We're going to do some problems right now because I'm not going to have time to go through series at this point. So, which is fine. We can do that next class. Let's do. All right, converge or diverge.
Right off the bat, you wanna know?
Well, I would hope you're going to try some stuff before you tell me, before you just randomly guess one of the two. Why? How do you know? Can't do that.
What was I wrong?
It sucked. No.
Yes, like a lot of these problems you're going to look at and go, "Oh, I know that." But there's going to be situations where what you know doesn't actually work the way you think it's going to work.
I just work in morning.
So what did I try with this one? Yeah. Okay. Almost right. Yes. I'll tell you why in a second.
Is infinity over infinity one of the forms?
Yes.
So you could do I split it up, the limit of the top one and the limit of the bottom one, they both came out to be infinity.
Correct.
So then you could take that derivative of top and bottom.
If I remember, literally, I just had to do this in the class today. That's the derivative. And then, like, I literally just thought that calculate. So so you're gonna end up getting ln of 4 to the n over ln of 9, 9 to the n on the bottom. Is what you're gonna end up with. Which will get rid of the 1. So it might make your life a little bit easier. But actually dividing it's going to be the easiest one here. You don't want to divide by 4 to the n though, because remember our goal is to get the denominator as small as possible. So you're going to actually want to divide by 9 to the n. So if we divide everything by 9 to the n, we get 4 to the n over 9 to the n over 1 over 9 to the n plus 9 to the n over 9 to the n. So what's 4 over 9 to the n go to?
0.
That goes to 0. What's 1 over 9 to the n go to? Plus 1. So this goes to 0. So converges. Yes.
Is if the 1 plus wasn't there, and it would end up being 0, there's 0, right?
If the 1 plus wasn't there, it was just 4 to the n over 9 to the n,
Yeah. Oh. Man.
you wouldn't have had to divide by it. So actually, we'll do this one because this one's a perfect example of what you just said. Well, perfect example of what you just said with one algebra step first. Negative exponents do what? You go to the bottom. So this becomes 3 to the n over 7 to the n. So my limit as n goes to infinity of 3 over 7 to the nth power goes to 0. If you didn't have the 1 there, you wouldn't have had to divide by anything because you just could have put it in one thing and been done with it.
Is 0 over 0? No, what now?
0 over 0 is still an indeterminate fact form, just like infinity over
So
infinity.
it's important to do the exponent rule to
Yes,
get the 7n out of there.
yes. Otherwise, you get 0 over 0.
That's the key step.
Actually, in this case, you get infinity or infinity, not 0 or 0. Okay. Let's do this one. All right. Figure out if it converges or diverges and how.
Divide by n over 2. Or sorry,
Yeah.
n squared, right?
Yeah.
That was supposed to?
So, because remember, one of the things that we can do, so we're looking for the limit as n goes to infinity of a sub n. But I can take this as the square root of the limit as n goes to infinity of 1 plus 4n squared over 1 plus n squared. I can take the power out. Remember, square root's just like a power. So if I add a 2, I can pull the 2 out. So I can find the limit of the piece inside of that, and that'll also help me get my answer. So yes, we could sit there and divide them all by n over 2. So we get the square root of the limit as n goes to infinity of 1 over n squared plus 4, 1 over n squared plus 1. So that goes to what? Square root of 4 over 1, which is 2. We did way too many. That came out to be 0, so I wanted to.
You know, like if you also just do long division.
That's the same question. Yes, you could. I don't know why. Um, don't make your life harder than it has to be. Yes, you could do long division there. There's no reason to. So, so this one, this comes out to be 2. I wanted you to realize that even though it doesn't go to 0, it doesn't mean it doesn't converge. This converges to 2. That's going to matter when we start looking at series. Okay, so a sequence can converge to something other than 0. All right, 2 more. Just because I want to torture you. I said just because I want to torture you. I did say that.
Abstain.
To Google chat.
No.
He said I can't stop. I
You're right. You can't cancel out a factorial. You can cancel out things in a factorial though. You just can't cancel out the actual the factorial symbol. What's factorial mean? Okay. So 2n plus 1 factorial equals what? Oh, hold on. That equals that, right? That's the same thing, correct? Okay. You're fine. You were exactly what I was going with, but I wanted to take one step at a time. That's the same thing, correct?
Why is that?
Because remember, factorial, 5 factorial is 5 times 4 times 3 times 2 times 1. It just keeps going down by 1 each time, right? So 2n plus 1, if I go down by 1, I get 2n, correct? If I go down by 1 again, I get 2n minus 1. So this is 2n minus 1 factorial over 2n plus 1 times 2n times 2n minus 1 factorial. Hey, guess what? I can cancel out a factorial.
We'll assume that was prevent.
Yes. One second, let me finish writing. And then I will answer your question. What was your question?
I don't think I'm 100% on the algebra.
Okay, so a factorial. Okay, so factorial is just all the numbers multiplied down to 1.
Yeah.
Okay, so, and they just go down by 1 each time. Right? Okay, so 2n plus 1 factorial is 2n plus 1 times 2n minus 1 times 2n minus 2 times 2n minus 3. I just keep going down by 1 every time. Correct?
Wouldn't you have to put the parentheses inside n plus 1?
No, it's 2n plus 1 is the inside the parentheses. So I'm taking that 2n plus 1 and dropping it by 1. So 1 less than 2n plus 1 is 2n. So there's 2n plus 1 minus 1. And then 2n minus 1 is 2n minus 1. Which happens to be what I had at the top as a factorial, so I stopped there. Now I no longer have a factorial. So if I take the limit of that, what does it go to?
0.
Right, because the bottom's getting infinitely large and the top's not changing. So a lot of this comes down to, back to what we were talking about, even with integration stuff, is manipulation of the problem to get to a point where you can solve it. All right, one more. So using your, just picking numbers, what do you think this is doing?
I didn't think box after like 6:15, I don't think so.
That's so real.
I've already been up and working.
Can you use the log rules here to put it together?
Yes. If you were just gonna plug numbers in to do this, you'd have log of 2 minus log of 1, log of 3 minus log of 2. You'd probably think it's going to infinity because you're just subtracting, but it's going to keep getting larger. 0. So, as you just said, that's that. Subtraction becomes division, which means this is that.
Copy and paste.
Yes.
What's the rule that lets you take the analog and get it outside?
It's in essence any of the operations you can pull out. I'm just trying to. I will find you the exact rule. I just can't remember which one it was in here. It's, oh, it's because I really didn't. I didn't actually put it up there. Is why. That would be why. This is the rule. It works as long as the function is continuous on the values that you're looking at. So typically, when you're looking at ends, since it's a sequence, n starts off at 1, goes to infinity. You're not dealing with negative ends and stuff like that. So ln is continuous on that setup because it's continuous from 1 to infinity, which is the value you should be looking at. All right. Series on Thursday. Oops, sorry.
Sorry, can you?
I hit the wrong button.
How does so the limit